Okay. Good morning, everyone. I want to believe those at the back can hear me clearly, right? You can all hear me clearly? Those at the back? Okay, thank you so much. I want to welcome you to another week, and of course, statistical machine learning class. What we're going to be doing from now actually going to be very, very crucial. And now we advise that you pay attention. Okay. The focus today will be on algorithms for partitioning clustering. So which means we're going to focus on a particular algorithm that we use to classify objects into different groups. And how are we going to do that? Of course, I will advise you pay attention. I want to welcome you to K-means. In the outline, okay, I'm going to talk about K-means. I'm going to talk about the algorithm that we actually use, okay, in doing this, grouping that I talk about. I'll walk you through the applications, the evaluation method, and what are the likely drawbacks. Then how do we implement this in R? Please pay attention, like I said. If you get stuck, ask me a question. I've been posting my videos on my YouTube channel. The last video has been posted. I'm also recording right now, but pay attention. Okay, I'm going to say this. If I'm interested in classifying objects into different groups without a prior knowledge, like no label, okay, then I'm actually doing clustering. I'm going to say clustering is one of the techniques in unsupervised machine learning. I remember earlier in the semester, I said we have supervised learning and unsupervised learning. The clustering that we want to do today, okay, can be classified under unsupervised learning because there is no label, okay? Now, when we talk about clustering can be divided into two. We have hard clustering, and we have soft. Please pay attention. When I say hard clustering, okay, the hard means a particular object can only be in one group. It cannot be, there's not going to be any overlaps. We do not want a situation whereby an object is going to be in group A and also going to be in group B. No. But that can happen in soft clustering. So what are the common algorithm for hard clustering? I'm going to show you. K-means is among them. Don't forget, today, the focus is going to be on K-means. But I first want to unfold, I want to let you know, okay, we got different algorithms that are classified under hard clustering. And what we mean by hard clustering is that, okay, the assignment is not going to be probabilistic. An object is going to be in one group. If you're in this group, you can be in the other group. Now, we have a K-medoid. It's another algorithm that we're going to talk about, which is also classified under hard clustering. We have hierarchical clustering. Our focus on Wednesday is going to be on K-medoid and hierarchical clustering. Okay, then we also have what we call the density-based spatial clustering of application with noise. But you know what? All of this, all these algorithms, they are classified under hard clustering. And what do I mean by hard clustering? It means object can only be in one group. Like if this particular object is in group A, this same object cannot be in group B. That's exactly what we mean by hard clustering. Okay, but you know what? I want us to focus, like I said today, we're going to be focusing on K-means. On Wednesday, it's going to be K-medoid and hierarchical clustering. And of course, On Friday is going to be on the density base of spatial clustering of application with noise and what I call the the generalized Gaussian mixture model. Let's get started. I want to say again, pay attention. Ask question when you get stuck. It's going to be getting tough. As we're going now, it's going to be getting complicated. But the moment you pay attention, you're actually going to be fine. Are you ready? You ready, right? Let's take a look at this. Now, if you see this side, okay, give me 1 second. I'm gonna use my pointer. Okay, if you make use of this, if you take a look at this side, these are the objects before we classify them into groups. Why are we actually trying to classify? Why do we want to classify objects into group? Because we believe objects are not the same. There's variation in stochastic world. And because of that, okay, we need to be able to use an algorithm, okay, that will classify objects into the group they belong. Take a look at this. This is after we have used k-means algorithm. So here, the algorithm is suggesting two groups. Is there any question with this? The algorithm is suggesting two groups that we call two clusters. Okay, that is what the algorithm is suggesting. But let me tell you this. If I want to classify, before object can be in the same group, let me tell you this. Naturally, every object is unique. I'm going to say that again. Every object is unique. Before I can classify objects into the same group, then it means, okay, intra-class variation is actually minute. They are classified in the same group. That doesn't mean they have everything in common. No. But what we're trying to say is that the distance between objects classified into the same cluster, that very distance is negligible. So when you take a look at this, right? If you take a look at this, I'm talking about if this is in the same group, of course, all the objects, they are not occupying the same position. There's still going to be some distance, but the distance is negligible. That is what we call intra, the distance within cluster. So the same thing here. But if you take a look at this, I have object classified into this group. We got another object classified into this group. What is the distance between object classified in one group and the object classified in another group? That is what we call the distance between clusters. And you know what we want to do? We want to maximize distance between objects in two different clusters. But we want to minimize objects. We want to minimize the distance between objects in the same cluster. Does that make sense? And that is exactly what we're trying to do here. Okay, I want to move. How does k-means clustering process? How does a k-mean clustering actually work? Now, I need you to pay attention. Okay, if I want to use k-clustering, if you take a look at that, we call that k-means. It means the very first step, you need to choose the numbers of your groups ahead of time. Oh, I think I'm going to use 10 groups. Oh, I'm going to use 5. Oh, I'm going to use 6. Oh, I'm going to use 7. Okay, the number of clusters is predetermined. You choose the values of k. And let me tell you this. After you've chosen, let's say I choose, maybe I want to classify I want to classify everybody in this class into 5 groups. Okay, ahead of time, I choose that number 5. Okay, then I will now randomly assign everybody into 5 groups. That is number 2 step. Randomly assign each observation into initial cluster. Okay, I'm assigning that into initial, cluster. And after that, when I assign you randomly into a particular group, I'm actually going to find the mean of each group. The mean of each group is called centroid. Centroid. That was called the mean of each group. Okay, that's what you see. For each of the K cluster, compute the cluster centroid. And you know what we're going to do next? How many centroid are we going to have? I mentioned the other time, 5 groups. I'm actually going to have 5 centroid. Then I'm going to reassign everybody again. I will assign you to a particular cluster, where the value that you have is very close to the centroid. I'm going to say that again. After having 5 centroid, the centroid here is like an average. Like you're having 5 means. That's what that guy is called K means. 5 means. Then I will reassign the observation. I will assign each observation into this centroid that their value is very close. And that is how. And when I say their value is very close, I'm actually going to make use of Euclidean distance in doing that. Okay? And let me tell you this. K means it's not convex. I'm going to say that again. K means algorithm is not convex. But with that situation under which it can be convex, you're going to see something now. Take a look at this. Because I want to minimize, please pay attention. You're going to be wondering, what is this guy doing here? Oh, this guy is actually want to do a job of minimization. Don't forget, I want to minimize the distance, okay, between objects classified into the same group. And that would be an optimization problem. Then I want to minimize the equation 1 here. What is M? M is the number of data points that I have. K is the number of clusters. Okay, W actually is the binary assignment. What we assign to group, that we assign you whether you belong to this group or not. When you belong to a particular cluster, WI is going to be 1. When you belong to a different cluster, it's going to be 0. Okay, but let me tell you this. What is the mu K? Okay, the mu K is like a particular centroid. The mean of a particular group. That is what mu K is about. Now, when you take a look at what we've done in the converse, if I want to minimize this, the only condition to attain global minimum is when this objective function is convex. You remember we did the condition the other time. I remember last week where we focused on the theory of convexity. But I'm going to tell you this guy is not convex. You're going to say, why? Why is it not convex? I'm going to say this. If there is no W, it's going to be convex. Or let me say this. If the assignment, what is doing the job of the assignment is fixed, centroid, it's actually convex. This guy is going to be convex. Don't forget, this is a square norm, right? On its own, that's a square norm. Square norm is convex. But this guy is discrete. I'm going to say that again. WIK is discrete. It could be 0 or 1. The combination of the discrete and continuous, because centroid is continuous. Okay, the combination of the discrete and the continuous is not convex. Go ahead. K is not a variable because we normally determine what we normally do ahead of the time. We talk about K ahead of time, but at the end of the day, okay, the system will still optimally compute K. But when I'm talking about convexity here, okay, I just want to tell you one of the drawback of K means. K means a lot need to be done, even though it is not convex. That doesn't mean it can't give us the global minimum, but a lot of effort. which I'm going to mention. But when you take a look at it the way it is, what is making it not to be convex is the combination of the assignment. Assignment is discrete. You know what I mean by discrete value? It can be 0 or 1. Okay, the combination of the discrete and continuous is not convex. But we're going to do something, okay, that will enable us to attain the global minimum. Okay, now take a look at this. We actually differentiate, but this is not necessary. You know why it's not necessary? Because before you can differentiate a function, it has to be continuous. But WK is discrete. Does that make sense? So it's always, even without this differentiation, you already know WIK, an object can be assigned if object belong to this group, to group K, and we assign it to group A with the weight assignment 1, and if it does not belong to group K, then I will assign it to some, another alternative cluster with assignment 0. Okay, the weight here is not continuous. The weight here is not between 0 and 1. The weight here is 0 and 1, which is make it hard. And that is why K-means is classified under hard clustering. There is no probabilistic assignment like a continuous one, where it's going to lie between 0 and 1. No, that's not what we mean. Now take a look at this. But we can differentiate with respect to mu k. Let me tell you this. That very function is actually convex with only centroid, because the centroid is continuous. Does that make sense? Okay, so what I'm doing right now, differentiate that with respect to the centroid k, and this is trying to tell you average, okay, is a good representative of the centroid. And that is why we call the algorithm K-means. Means, it relies on the power of mean. The optimization here is confirming the fact that I can use mean to represent centroid. Now, I'm actually moving. I'm going to go into this example. Please pay attention. I have an image. I want to apply K-means algorithm in compressing image. Why am I compressing image? Because this image, if you take a look at the one here, the initial image, of course, this is beautiful. It gives a lot of information. It's detailed. But you know what? It occupies a lot of spaces. We do not have unlimited storage facility. So how can we reduce the dimensionality in this image in such a way that the quality of the image will not be totally lost? Then we can actually compress. Please pay attention when you take a look at this. This actually contains millions of colors. The pixels here, the pixels color is millions. But you know what we want to do? Oh, I'm seeing those millions of colors as student in this class that I want to classify into just 6 groups. Can I have a way to classify millions of color into just 16 colors? When I say 16 colors, I'm saying this. I'm actually going to have 16 centroid, where each centroid is the mean. And that very mean is the mean of several colors in that category. So what am I doing here? Instead of millions of colors, I'm actually using just 16. And at the end of the day, and if I now want to do that, before it's going to arrive at this 16, there's going to be a lot of iteration taking place. Please pay attention. Can you see something running? Can you see that iteration? It's going to start from 0, 1, 2, 3. And why do we need that iteration? I'm going to tell you right now. Now, because the objective function of K-mean is not convex, and in order for us not to get trapped in a local minimum, we want a global minimum, then we need to have a very good initialization strategy, and we're going to do that many times. And that's why, can you see that now? And at the end of the day, is likely going to return. Okay, 16 images is enough. 16 central is enough. Whether that is enough or not, we have a way to evaluate. Whether that is enough or not, we have a way to evaluate, okay, the optimality of the results. Okay, so when you take a look at this, the compressed image is not as detailed, it's not as beautiful as before, but we have not lost total information. Okay, but we have saved our storage space. Does that make sense? So k-means is actually used, we use this in to compress image, also used in face recognition. Okay, now if you take a look at this, that's an iteration. You see the rate that is running. Okay, it's an iteration since it's going to run for several times. Okay, so what you're actually seeing now, we are actually having an image. You have a boundary line. You see the boundary line, trying to give you a picture of three groups here, or three clusters. This is a different one. Okay, I'm moving. How do we evaluate? Let me tell you this. Even though we're going to start with an initial value of k, but at the end of the day, we're actually going to end up with an optimal values of k. Okay, also the optimal values of k. How do we actually, if I want to figure out whether I should use 2 clusters or 3 clusters or 5 groups and so on like that, then we have what we call the modules, or we have techniques of evaluations. We got number one, we got elbow. I want you to take a look at this elbow now. Okay, it's one of the method of selecting an optimal numbers of clusters. Now, this is a plot of the average expansion against the number of clusters. Of course, everybody know k equal to 1 means I've not even started with my classification. Everybody is still in the same group. If everybody is in the same group, of course, we expect the distance, the dispersion to be high. That's what you're seeing here, right? And as time goes on, when you try to increase the numbers of clusters, we expect the average expansion to also be going down. But we actually want to identify, the optimal number of, what k is actually going to be. Okay, so this is what we call the within variation. Because let me tell you this, we want to minimize the within when I use a cluster 1, okay, I expect if I use 1 cluster, I expect within variation to be more than when I use cluster 2, and so on like that. Now, this is an elbow, okay? So when you take a look at this now, based on this elbow, it may be suggesting that, okay, why can't you settle for 3 or settle for 4? Okay, now we have another one that we call Silt coefficient. But let me tell you this. The Silt coefficient actually will enable us to guide against overfitting. Okay. The slope coefficient we can trust slope coefficient more than the elbow, because when you take a look at the elbow, okay, people could observe differently. My elbow may not be your elbow. So that could be confusing, right? Okay. But when you take a look at this guy here, okay, it's actually going to return a slope coefficient. The slope coefficient is going to go from -1 to 1. When your slope coefficient is very close to 1, what are we talking about here? I have classified objects into a particular cluster, and I want to be able to investigate a slope coefficient for object classified into a particular cluster. I really want to see whether I want to measure the degree of compactness. I want to see how am I so sure this particular object should be in this cluster. So now, if the value return close to 1, then that is an agreement. If it is very close to -1, that's a disagreement. It means the object should be in a different cluster. And that was why I said, this is a measure of the goodness of a clustering configuration. This evaluates how well each data point fits into the assigned cluster. Okay. And I said, where a high positive value will indicate a well match. Okay. A high positive value, which is very close to +1. Okay. We actually indicate that, and a low or negative value will indicate, that we have issue here. Okay. Now, this is an example. How many colors are you seeing? How many? How many colors? 5. Is it 5? Thank you. Do you know initially we have 18,941 samples. 18,941 samples have been, partitioned into 5 clusters. And of course, I can measure, the slot coefficient for each. If you take a look at this color and this color, the slot coefficient is going to be higher than the others. Okay, if you take a look at what I'm saying now. Now, I'm going to go to another one that we call gap statistic. Okay, we do not have just a single measure of doing this. We actually have, we make sure we have more than one evaluation criteria. I talk about able, I talk about slowed, and I'm talking about gap statistic. Okay, but let me tell you this. If you take a look at the first and the second, the able and the slowed, that is not statistical enough. But the gap statistic is statistical enough. Okay, but let me tell you this. How this actually works. Okay, the gap statistic. Okay, the expected value will be determined. We're going to determine the expected value, by generating a large amount of reference data. But yeah, I'm going to show you. We're going to say, oh, that follow uniform. The non-hypothesis is going to say it's follow uniform, and the alternative is going to say it doesn't. But you know what? I want to walk you through an example now. How do we compute K-means algorithm in R? And I'm actually going to use, so in the data preparation, whatever data that you're actually going to use, of course, the data structure is going to be arranged in row and column, and make sure there's no any missing observation. When observations are missing, okay, you have to have a way to deal with that. Say that you estimate it, or you have a way to deal with that. How software can help with missing observation. Okay, and let me also tell you this. If I have variables, because the variables are not necessarily to be in the same scale, we don't want a situation whereby one particular variable will dominate the other. Because of that, we need to standardize. I'm going to say that again. We do not have a situation where among the features, a particular one will dominate the others. Because of that, we're going to scale. Okay, standardizing our variable is to make it to restrict the mean of all the variable to 0 and the variance to 1. Has anybody heard about standard normal distribution? Okay, thank you so much. Now, I'm actually using this data set, US arrest data. Okay, this very data, we collected crime variables across, 50 states in the United States in 1973. And of course, we have the crime variables like murder, rape, and assault. And the fourth one is actually talking about the percentage of population living in that particular area, making 4 variables. Okay. Now, let me tell you this. The variables, from what I've seen, let me quickly take you to the variable. From what I've seen, assault is going to dominate because the rate of assault is more than the rape rate, is more than the murder rate. And that is why. So this is the data Although it's more than this, in R, I'm only showing the first 6 for the first 6 states. Don't forget, we have this data over 50 states. So as you can see right now, okay, if you take a look at the assault, can you see the value for the assault? It's higher than all of that. Now, this is represent the arrest per 100,000 residents. Each of these variable arrest per 100,000 residents. Okay, and we added urban population. Okay, the urban population here is percentage of population living in a particular area. Does that make sense? Now, there's something I need you to, what are the necessary library do I need to load in R before I can actually successfully apply K-means algorithm? Then you need to first load these packages. Tidyverse for data manipulation. Okay, the cluster for clustering algorithm, and of course the FactoExtra, for clustering algorithm and visualization, because we're going to do some visualization work. Okay, and of course if you write this code now, the name of the data is USARS. If you copy this into R, you're going to see your data set. Okay, this guy NA omit means that is how to deal with the missing value in R, because we don't want, your K-means algorithm actually require you to have a complete data set. Does that make sense to everyone? Okay, now if you take it, this is the original data set. I'm only showing 1 to 6 states here, from Alabama to Colorado. Of course, the data set is 50. We collected this across 50 states. Now, the way it is, I'm not going to apply my K-means immediately. I need to scale, because I don't want a situation or where a particular variable will dominate the other. And as you can see here, assault rate is more than moderate and the rape rate. And that's why we need to scale them. This is after scaling. Okay, you can see scale is to restrict the mean of each variable to 0 and the variance to 1. We want them to be on the same scale. Okay, and this is the first 6. After scaling them, take a look at what we have right now. Of course, some is going to be 0 something, some is going to be -1, and so on like that, as you can see. Okay, now let's first get some. Can we have a way to first generate what I call its map? Let's do some visualization work. Okay, can we have a situation where we can look at the relationship between any 2 states? Well, putting into consideration the crime variables. That's exactly what you're seeing right now. So this is what we call its map. If you want to look at the the relationship between 2 states, with the respect to the crime variables, that's exactly what I mean. Okay, and of course you're actually going to you're seeing different colors now. Okay, you're going to see the red and orange tones. The red and orange tones here have the high values. Okay, while the other color have the low values. This is where I actually want to compare 2 states, and one at a time. I actually want to see, is there any relationship between the 2 states with regard to crime variables? But you know what? That's not where I'm going. Now, I need you to pay attention. What I want to do now, I remember the other time when I started this course, I said addition will drive some questions. One of the questions here, we actually want to classify states in the United States into categories, putting into consideration, crime variables. That's our intention. If I want to start, this guy is saying, can you start with just two groups? Here I'm trying to say center equal to 2. Okay, N start equal to 25. Don't forget, I'm going to have that many times. Okay, because don't forget the objective function with the K-mean is not convex, and we actually need to have a very good initial strategy, initialization strategy, and do that multiple times. Okay, we're choosing to do this 25. You can say n start equal to 25. Now, for two categories, this is the result. Now, this is, you can see cluster 1, cluster 2. What you are seeing here, we represent the average, like this is the average for murder in cluster 1, the average for assault in cluster 1, average for the urban population in cluster 1, the average for rape in cluster 1. So this is just giving the cluster means. So this is like we have succeeded. We're going to have some states in group 1. We're going to have some states in group 2. And we're going to be using this statistic. This statistic is common to all the states, classified in a particular group. That's exactly what we mean. So here, K equal to 2. Okay. Now, but if I want to know the sizes, if I want to know, oh my God, Ari is trying to tell me here in the group 1, we got 20 states. If you also want to see the state, okay, you can also gonna have access to those states. And in group 2, we have 30. This is when I use 2 center. But you know what? If I want to look at the states, okay, I'm actually going to do this. You can see when I do that, oh my God, this is the 2 clusters that I'm talking about. Look at in each cluster, you can see the state. Oh, where is Minnesota? Can somebody find Minnesota here for me? Oh, here, right? It's in blue, right? I think Minnesota is around, let me see, the bottom right, like maybe here, right? Is it here? I think Minnesota and Wisconsin, I can see them together. Look at that here. Okay. This is when I use when I use 2 groups. But let me tell you this. These 2 groups may not be optimal. Okay. Now, I'm actually going to do something again. Now, you know what I want to do here? I've used 2 groups. I also want to use 3 groups. I also want to use 4 groups. I also want to use 5 groups. When I use 2 groups, when I use 3, when I use 4, when I use 5, then the able method that I showed you the other time, the gap statistic and the slope, they can tell me which of that is optimal. Okay, now you know what? This is the code. Now, if I want 3 groups, if I want 4 groups, if I want 5 groups, okay, now let's now draw. This guy is, I want to plot that. Okay, now plotting that. This is for the 2 groups, this is for the 3 groups, this is for the 4 groups, and this is for the 5. But right now, how do I decide? Okay, how which of this is the optima? Then that is going to take me to another story. Oh my God, the statistical machine learning is about story. We don't just do what we do. We got a reason why we do what we do. Now we have 2 categories. We got 3 categories. We got 4 categories, but we got 5 categories. We now want to choose which one is going to do the job, and that is why we need this 3 method. This is for evaluation to determine the optimality, okay, in terms of the number of clusters. But let me tell you this, if you want to do this, there's something that we're going to compare that we call, if you enable, okay, if you take a look at this guy, for the able, we're actually going to have a plot of within variation, within class variation, okay, we're actually going to settle for the cluster with the minimum within class variation. Okay, so this one is good. But if we're doing that, make sure you set seed. You can see here I set seed and I put 1, 2, 3. That is for reproducibility. Because don't forget, we are running this several times. Okay, if we don't set the same seed, we're not likely going to have the same result. So we set the same seed so that we can have a uniform. Now, this is for the able, this is for the slowed, this is for the gap. Let's take a look at the picture. Look at that. Okay, based on this, can somebody tell me, using able, how many clusters? Okay, you said 2. Thank you. With another person? Somebody said 2. 2, 4. Okay, 2 or 4. 2. Okay. Now, that is one of the drawback. You are all correct. And that is one of the drawback using able. My observation may be different from your observation. Actually, this is 3 or 4. Because when you take a look at this, when the cluster is increasing, okay, when the cluster is increasing, okay, the within variation is going down, but it's going to get to a point where it's going to slow down, okay? And that's actually occur between 3 and 4 here, okay? But let me tell you this. Situation where the data is noisy, when the data is noisy, you can trust, able can be trusted, cannot be trusted. Okay, let's take a look at this guy. Look at this. Look at this one. Okay, this is very obvious. You say k equal to 2 because you know why? This we're actually going to choose the number of clusters that correspond to the maximum slowest score. You know the maximum occur here. Can you see that? This guy is saying k equal to 2. But let me tell you this. Slowest method actually has an history of choosing fewer numbers of clusters. You can see that? And that's why those who judge, they are not right at all times. We're using this to judge. They also have their own drawback. Does that make sense? Now, let's go to the next one. Gap statistic. What is it suggesting? K equal to 4, right? The gap statistic. Let me tell you the advantage of gap statistic over the other. Okay, this will safeguard against overfitting. With against situation whereby the algorithm will perform excellently on training data, but will perform poorly on unseen. So this is going to guard against that. But let me tell you this. This is suggesting 4. Ebo is suggesting 3 or 4, and the slowest is suggesting 2. Okay. Now let me tell you this. Situation where the 3 agree. Of course, that's a perfect optimality. But situation where they don't agree, then it now depends on your intention. But most of the time, we prefer the gap statistic. Okay, now, because of that, I'm going to base my final module analysis on the one I choose. Now I choose k equal to 4. Then I'm going to, don't forget, I've choose k equal to 4. Okay, don't forget you have to set seed. If you don't set seed, okay, setting seed is for reproducibility. Okay, so if because if you don't set seed, okay, if you are working on this same data, you're actually going to get different results. Okay, we want the result to the uniform. Okay, now because we're told that from what we're seeing, 4 clusters is going to be okay. Now when I perform my analysis on that, this is what I'm actually going to have. Now here, this here classify the state into 4. Okay, for each state, this guy here, for all the state classified into cluster 1, you can see the mean for the murder rate, for the assault, for the urban population, for the rape. For those classified into 2, you cannot see that. If I don't want to view that, this is it. Take a look at what I have now. Oh, where is my Minnesota? Somebody should find my Minnesota. How? Where's my Minnesota? In the red. Oh, bottom in the red. Thank you. It's right here. It's like Minnesota and Wisconsin. They follow each other. So take a look at that. Okay. So what we have done here, we have actually using we've actually used k k equal to 4. We believe that in classifying state into groups according to crime variables, okay, we should have 4 groups. So what is the implication in the policy formulation, which means the same strategy can actually be used, if you're to bring down crime rates here. Does that make sense? That is what it means. If they are in the same group, okay, so Minnesota can decide to use the same strategy used in Wisconsin for crime, to reduce crime. Okay, Alabama and Georgia can use the same. Look at that, because they belong to the same category. Florida, Michigan, Texas, Maryland, and the like, they can use the same, strategy in reducing crime rates. And I told you the other time, you can see what we've done today. If we actually, we need information, we need knowledge to be able to answer some question. And right now, if I have so many states, okay, and I collect the state across several crime variables, I can actually classify state into categories. And you know what we're going to do next? What we're actually going to do next, instead of us to actually use a mean, don't forget, this is called k-means. We are the center of a group is actually the mean. Okay, so that we call centroid, but mean is sensitive to outlier. According to Benkamp in 1982, outlier is a data point, a particular data point that is not consistent with the rest. And the moment outlier is present in the data set, is going to make the data set noisy. And you know what? K-means, that is one of the drawback of K-means, because mean is sensitive to outlier. And that is why in the next lecture, we're going to talk about K-medoid. The K-medoid, you're going to say, instead of me to use mean, I'm going to use something else. And I'm also going to talk about hierarchical clustering. That's what I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.